Okay, welcome back everyone to the last part of the introduction lecture on density functional theory. And in the last part we will discuss the Kohn-Sham formalism, or also sometimes called Kohn-Sham DFT, where we discuss the functional dependency of the kinetic energy, which we left previously open in our discussion of the Hohenberg-Kohn theorem. And that will us provide with a full explanation, a practical explanation how to solve DFT, and then in the second part of the DFT lecture, which takes place next week, we then discuss practical aspects, how to use DFT. But starting with the Kohn-Sham DFT, let's introduce Kohn and Sham. I mean, Walter Kohn I already introduced to you in the Hohenberg-Kohn theorems, but I should introduce you Louis and Sham. Together with Walter Kohn, they formulated a year later than the Hohenberg-Kohn theorems what's nowadays commonly referred as a Kohn-Sham density functional, so the modern implementation of DFT. What they did is that they provided a solution for the functional dependency of the kinetic energy by replacing the complex many-body particle problem, which we had beforehand, with a single particle problem. So solving that kinetic energy contribution had been done previously by Thomas and Fermi, for example, but they couldn't really achieve what then later Kohn and Sham did. So the idea is that we have a non-interacting electrons in an effective potential. So we go basically from, I lost all my arrows, sorry. So we have an interacting potential going like that, something like this. So I'm not great in drawing, to non-interacting electrons in an effective potential. And this effective, sometimes also called auxiliary potential, is the same for all electrons. That's quite important. And with that we can formulate the dependency of the kinetic energy with those non-interacting electrons, which become this expression here. Whereas now our electronic density consists out of single particle wave functions, right? Before we had the electronic density consist out of the system wave function, and now we only have it as a single wave function, a single particle wave function, sorry. And the assumption we are taking here is that the true ground state density of an interacting electronic Hamiltonian can also be represented as a density of an effective single particle Hamiltonian. And that's a bold statement, right? It might be true, but it don't has to be true. And it's a good approximation. So in contrast to Thomas and Fermi, what Kohn and Sham did by this taking non-interacting electrons into account is that they realized that solving that problem for interacting electrons is quite a challenge, and Thomas and Fermi failed to do that. So Kohn and Sham said, okay, when we can't solve that, then let's try at least to go as close as possible. And that's what they came up with their solution. They completely accounted for there might be a small difference between the true kinetic energy and our kinetic energy contributions. But as long as we're close enough, that's actually quite decent. And that's basically their achievement. So if we know, shifting from the Kohn formalism, right, to the Kohn-Sham formalism, we see that the first term is our Kohn-Sham kinetic energy. That's our external potential. That's our electronic contribution, so electron-electron interaction, which we discussed before. And that's the exchange correlation, where we previously in the Kohn formalism put all our self-interaction, exchange and correlation contributions into it. By doing that shift, going from Kohn to Kohn-Sham, we basically end up with something called the Kohn-Sham equations. So the true ground state is now obtained by minimizing the Kohn-Sham energy density functional, and by variation of a single particle wave function, we basically end up with the Kohn-Sham equation, which are shown here. And that's basically a single particle Schrödinger equation with an effective single particle potential, right? The term in brackets is our Hamiltonian. That's our wave function. That's our eigenvalue, and that's the wave function again. And now the wave function is a single particle wave function. So that equation looks exactly like the Schrödinger equation, but for a single particle. And in the practical use cases now, we solve that single particle Schrödinger equation for a many-body system. And that's how we apply, and that's basically how we use DFT, then what we discussed next week. One final comment to the Kohn-Sham equation. So we have our Kohn-Sham eigenvalues and our Kohn-Sham orbitals, which are those single particle wave functions. And it's quite important to understand that neither the Kohn-Sham orbitals nor the Kohn-Sham eigenvalues have a physical meaning. We will discuss that in the next lecture at the end a bit. We can contribute, or we can get some physical meaning out of those values, but in principle they have no physical meaning and should be not equated with the post-Hartree-Fock orbitals or energies you get out of whatever post-Hartree-Fock method. That's quite important to remember. And we leave with the Kohn-Sham equation with a self-consistent problem. Because the electronic density determines the effective single particle potential, so we need to solve the Kohn-Sham equation iterative, which we will discuss in the next lecture as well. So now with a final word to this exchange correlation functional. We had it quickly when we discussed the Kohn formalism, and now I want to make a final claim on that. So the exchange correlation functional acts as a place where we put everything in we can't calculate. So if you want to be a bit rude, you can say it's like the DFT's garbage bin. So that's the exchange contribution, and that's the correlation contribution we already got from Hohenberg and Kohn. And now what I said with the Kohn-Sham formalism is, right, we get the kinetic energy from Kohn-Sham based on the non-interacting electron description, which don't need to be necessarily the true kinetic energy of a many-body interacting system. So there might be a difference between Kohn-Sham's kinetic energies and the true kinetic energy, and that's also included into this exchange correlation functional because we don't know how to compute it, so we put everything together in this exchange correlation contribution, right? As I said, it's the difference. And then And because we don't have any, or at the moment we don't have any solutions how to solve those three different contributions, we approximate them, where different approximations are available with different accuracy, which we will discuss in next week's lecture. And that's where we end the Kohn-Sham formalism. And to round up the whole lecture, we discussed 5 different topics, right, where DFT comes, or what DFT can do and what DFT can't do in this materials modeling scheme. We discussed the fundamentals of the Schrödinger equation and the Born-Oppenheimer approximation. We then did the transition from the wave function to the electron density. We then discussed how the electronic density is determined by an external potential and sets up the true ground state energy in terms of the Hohenberg-Kohn theorems. And last but not least, we discussed the Kohn-Sham DFT, how to solve the kinetic energy contribution to set up or to leave us with the Kohn-Sham equations, which we then solve in practice, which corresponds to this single particle Schrödinger equations. So in conclusion, DFT can be used to determine electronic and atomic structures of a material containing up to 1,000, right? It's more like 500,000, you find sometimes both numbers, of atoms sizing from 0.1 to 10 nanometers in length. The Schrödinger equation cannot be solved exactly for most of the interesting systems. I mean, hydrogen is quite nice, don't get me wrong, but only solving hydrogen might be a bit boring, so to say. So we need to make approximations to solve it in practice. Using the electronic density is a valid approach to describe the true ground state of the system. We discussed that from the transition from electron to density. And last but not least, I can't point it out as often as possible. DFT is in principle an exact theory. We didn't took any assumptions, right? I mean, we used the Born-Oppenheimer approximation for practical use, but we don't make any assumption on the way formulating DFT, right? I mean, at the end we end up with 3 terms we can calculate, and we end up with a term we can't calculate, basically, with the exchange correlation contribution. But that's more practical use. So in the formulation scheme, we don't use any assumptions. So from that perspective, it's a exact theory. Even then, the practical application is not exact theory. I agree on that. Okay, with that, we are at the end of today's lecture. Thanks everyone for listening, and then we see next week with more practical applications, more like going from the pure theory as discussed today to the practical approach, how to apply DFT actually to systems and to answer research questions. Thanks everyone.